Dear learners, welcome to the course MSD012 Ecosystem and Natural Resources of the program Postgraduate Diploma in Sustainability Science. Now, in the last session, we have talked about energy and its different components and what are all those energies, different types of energy. Today in this session, we will touch upon mineral resources. We know that our life, it is accompanied by mineral resources at every step, and use of these minerals by human beings has been so extensive since the beginning of human civilization. And if you look into that, how we are more at ease to depend on the particular different mineral resources, you will find that in the history, in our history and the prehistory era, sometimes those era is means named after minerals. For example, we have the Stone Age, we have Bronze Age and Iron Age. Today, we ourselves tag it as a Iron Age, but if you look into the resources we are using, we can say that we enter the age of silicon. Because if you look into the that ICT, we are more dependent on that ICT, computer, and so on. They are entirely depend on all those semiconductors. And so, if you look into the electronics gadget, we are depending on this era. So, silicon is one of the important metal in the production of semiconductors. So, we can assume that we can say that we are in the era of silicon, right? Then when you talk about mineral, the question comes, what is mineral? And we know that mineral resources, they refer to material substances either composed of or extracted from the minerals, right? Now it includes, ores, metals, gravel, sand, marble, granite, phosphate rock, and so on that we have seen in front of us. Every activities they contain one or other form minerals, right? So these are actually, all these minerals are actually inorganic compounds, and some of them, we find that they are deposits. They may be concentrated or accumulated by life form. For example, limestone, and that is composed of this limestone is composed of calcium carbonate shell of sea glaciers. And as I told everybody knows that we find minerals in large number of ways in everyday in our life. Like if you look into domestic sector, also from the morning to evening, we entirely use most of our products are entirely based on mineral resources. You look into agricultural sector, you look into industrial sector, in commercial sectors also. So in that way, minerals have become very essential, in development of industrial plant and machinery. Then when we talk about energy, generation of energy is also entirely depend on minerals like koila, that lignite, uranium. Then construction of housing, then road, infrastructure, that's also depend on energy. If you look into defense sector, means that's also, weapon armaments are made of these minerals. And even as we talk about communication era, then that's entirely depend on minerals like telephone wires, cable, electronic devices. If you look into health sector also, most of the Ayurvedic system, then they are particularly depend on, and also they contain this minerals component. So if you look into the alloys of various purpose like phosphorite, they also contains of this a kind of minerals. So then if you look into agriculture sector, like whatever we are depending on fertilizer, seed dressing, fungicide, all these contain minerals in the form of chemical or non-chemical, right? Like, one of the important is who is very precious is jewelry. These gold, silver, platinum, diamonds, they are high graded minerals. So this mineral wealth is a natural asset that can stimulate or enhance economic growth potential and social progress. That is No, that is how sometimes we know in our prehistory or history period we name it that era in different form. We tag names of minerals as that era, right? So if you look into the reserves of metals and the technical know-how to extract these resources, that is the key elements in determining, the economy and political power of nation. At the same time, we know that the world is facing serious and long-term challenges in provision of these mineral energy resources. Although no global shortage of non-ferrous mineral resources are expected in the near future, but there are a growing number and variety of obstacles that we have seen in front of us. So, if you look into those issues, these are very complex issues that comprise of economic, technical, social, environmental challenges. That's why, as a student of sustainability science, we need to understand, aware about these mineral resources. So today in this session, we are trying to understand in brief about the increasing mineral demand and the scarcity of mineral, the pattern and causes of mineral demand, and how, when we talk about all these causes, impact of using of these mineral resources, there is a need to understand how mineral deposit, ores and reserves, what kind of extraction process we follow in extracting those mineral deposit, ores and reserves for our economic use and for our efficient use. So if we look into the increasing mineral demand is scarcity of minerals, before coming to to know about the different types of minerals, as a student of sustainability science, we need to understand why we need to study this. We know that before the 19th century, that global use of mineral was relatively insignificant compared to the abundance of mineral in geological deposits. Because when there is enough resources, we don't care about that. So even if you go back to the Industrial Revolution, then suddenly there is with the associated phenomenon of demorphic means demographic plus technological development, and that highly enhanced rate of mineral resource uses. So in fact, what we can say is that after Industrial Revolution, suddenly that rate of mineral resource uses increases. So in fact, if you look into some of the evidence from this fact is that the world's population has doubled. So when population is doubled, what happened? The mineral use has increased by a factor of 10. And especially with the evidence, if you look into the human history during 1750 to 1900, that with the double increase in population, then by factor of 10, that mineral use has been increased. So the mineral use at present means in this during the decade is more than 13 times the amount use that used to be in 1900, right? So the demand for mineral is, as we know, is still extremely high, and it will increase further with industrialization, especially in developing countries and underdeveloped countries. So on the other hand, we are replacing of aging infrastructure, and we are also trying to introduce new technologies looking into the issues of sustainability. So this shows that the increase in demand will be increasing. So again, if you look into the life expectancy of a stock, if it is not linearly related to the increase in the stock, that is, for example, a 10 to 100-fold increase in the stock doesn't mean that the stock will last proportionally. So if you look that theoretically, in a theoretical situation, let us assume that future exploitation will continue at present rate and demands remain the same. Then the life expectancy of a stock can be linearly related to the increase in the magnitude of the stock. In such situation, in such theoretical situation, the stock means the reserve is called static reserve. On the other hand, another kind of that particular reserve we call this exponential reserve, when the demand generally increases exponentially due to increase in population and per capita consumption, and the life expectancy of a reserve decreases exponentially, right? So when but if you look into this exponential and this static reserve, exponential reserve are more realistic as they better reflect the real world pattern of demand. The demand for metals such as tin, zinc, copper, aluminum, they grows at about 1 to 4% per year. If you assume that demand is increased by 3.5% per year, then annual demand will double approximately in every 20 years. So a stock having a static reserve of 500 years may last only 83 years when exponential rate of exploitation is taken into account. If we talk hypothetically, 500 year static reserve is increased to 5,000 years, the exponential reserve will increase from 83 years to only 147 years. So the bottom line is that on a global scale, the demand for mineral resources now are so great that even with a conservation of liberal estimate of remaining mineral stocks, the known supplies of a number of minerals will be exhausted within a few decades. So then what will the effect to the environment? The effect will be the environmental degradation and its associated pollution of mining activities that force us to curtail the exploitation of mineral deposits before they are exhausted. So what we can do is we need to emphasize the 3 R's, as we know: reduce, reuse, recycle, as well as we need to find a substitute for mineral in short supply, right? So then this is a situation why we need to understand what are the minerals, how the extraction process is that, right? So let us look into what are the mineral deposits, ores and reserves. We know that a mineral is a naturally occurring solid chemical substances that is formed through a geological processes, and it has a characteristic chemical composition, highly ordered atomic structure and specific physical properties. And we know that this mineral range in composition from pure elements and simple salts to very complex silicates with thousands of other forms. Like when we study about sustainability, we call that subject as sustainability science. In the same way, the study of minerals is called mineralogy. So, and mineral deposits, they are formed by natural geological processes, right? So, during the rock cycle, the weathering may dissolve or physically remove certain elements and minerals that leaves behind a concentrated residue to the remaining minerals. So, then it follows sedimentary processes. In sedimentary processes that can concentrate minerals to precipitation from a solution or by differential settling of grains in moving or in still water, moving water or still water. At the same time, we know that certain minerals may selectively crystallize out of a hot molten body of igneous rock. So during the formation of metamorphic rocks, elements may be mobilized in the rock, resulting in mineral changes, and sometimes it gives rise to economically useful mineral concentration. On the other hand, in certain elements, the high temperature associated with this igneous and the many metamorphic process that result into hydrothermal processes. That is a process when hot water dissolves, transport and subsequently reprecipitates and concentrate elements, minerals in deposit. So the abundance and distribution of minerals are very uneven, as we know. On a global scale, only few elements like oxygen, silicon, aluminum, iron, calcium, sodium, magnesium, potassium that are extremely abundant, making about over 99% of the earth crust by weight. But in the same time, some other elements like copper, tin, etc. are very rare. Again, if you look into most of the mineral deposit, they are not usable and its supplies are particularly exhaustible for abundant rare minerals. Okay, so when we are trying to understand how it was extracted. So then how we have to follow those processes. So a mineral deposit, it has becomes an ore deposit at certain point of time when the mining and the processing of the mineral becomes techno-economically feasible, means that is a mineral deposit of today may become an ore deposit in some day. So when we identify but unexploited ore deposit are called as reserve. So one is ore deposit, another is reserve. So reserve estimates for a particular mineral that will increase as new ore deposit that come into existence. As the mining and the processing technologies become more efficient and improved, or as price rises, allows mining and processing of lower grade deposit happen, right? So reserve estimates will decrease as non-deposit of a particular mineral are exhausted, or if market prices fall to discourage the mining of lower grade deposit. So at current consumption rate, as we know that iron and aluminum and earth crust could last 1 million years and 100 million years respectively if we do not follow any of the recycling process. So it seems that virtually it is inexhaustible, but at the present rates of consumption, the proven ore deposit of iron and aluminum will last only for a few hundreds to a couple of thousand years, right? We know that many substances are very rare. For instance, copper has an average concentration of only 55 to 63 parts per million of the Earth's crust, and tin only 2 parts per million. There is an upper limit to the quantity of minerals that can be produced, even if energy supply is made unlimited. However, practically, if you look practically, our energy resources are limited. And taking into the world production, consumption and reserves into account, it has been estimated that our virgin supplies of ores for copper, tin, lead, zinc and various other metals will be exhausted in another century. So what are the types and grouping of those minerals? We know that mineral deposits are diverse in nature and composition and that reflect their origin. It can be divided into different categories such as metallic, non-metallic, and precious and energy metal. When you talk about metallic minerals, it includes which are very common, that are iron, aluminum, copper, zinc, lead, gold, tin, chromium, and so on. So these metallic minerals, they can be ferrous, means iron and related metals such as chromium, manganese, nickel, molybdenum. They are very common alloyed with iron, or non-ferrous like gold, copper, silver, etc. In case of non-metallic minerals, that can be similarly be divided into structural materials and industrial materials. When you talk about structural materials, they are building stone. They are used for building stone, sand, and then we have sand, gravel, and other component of cement and concrete. So when you talk about industrial material, it is, for example, fertilizer component, phosphorus and potassium, salt, sulfur, other metal used in manufacturing, asbestos, abrasive mineral, and so on. These are how non-metallic minerals can be classified. Then coming into the third category is the precious minerals, such as gemstone and semi-precious minerals that serve no pragmatic function and are purely of ornamental and aesthetic values. Finally, another category is energy minerals. That's of uranium and fossil fuels, about like coal, oil, natural gas. Alright, they are fourth category of energy minerals. So we know that due to unequal distribution of mineral deposits around the world and depletion of once existing deposit, many countries have a small or non-existent reserve of certain important minerals. Such kind of certain minerals which are necessary for the production of essential goods, they are again further classified as critical minerals. Then another classification we take into account is strategic minerals. When a critical minerals or a mineral is called as a strategic mineral, that when a particular country or countries, they must import from areas that are potentially unstable, politically, militarily, socially. So problem in these areas could disrupt the supplies of such minerals. So that's kind of mineral which is important in that particular country is called strategic mineral. So critical minerals may or may not always have substitutes, and sometimes the substitutes are rarer than the critical minerals themselves. So in order to have a better understanding of the mineral deposit effective exploration, they are subdivided into different categories. Then the classification can be done based on a number of criteria, right, such as mineral or metal contents, the shape or size of the deposit, host rock means the rocks which enclose or contain deposit, or the genesis of the deposit means that geological process was combined to form that deposit. We know the on the other hand, based on the major anion group present and in approximate order of their abundance in the earth crust, we follow the classification of the minerals in different way. One of the famous classification in Dana classification system is Dana classification system. In Dana classification system, the minerals can be classified into 9 categories. Number 1 is silicate class, carbonate class, sulfate class, halide class, oxide class, sulfide class, phosphate element, and organic. When we talk about silicate class, this is the largest group of minerals by far. Then these are composed largely of silicon and oxygen with some parts of aluminum, magnesium, iron, and calcium. And if you look into most of the rocks, they are 95% silicate, right? Example of this category are feldspar, quartz, olivines, pyroxenes, amphiboles, garnets, and micas. Then second category is carbonate class. Here in carbonate class, the major anion is carbonate. This includes minerals of calcium carbonate, that's of calcite and aragonite, magnesium calcium carbonate, dolomite, iron carbonate, siderite. So carbonates are very commonly found in marine setting when carbonate containing dead organisms settle and accumulate on the sea floor. They are also found as evaporate deposit in some of the lakes like the Great Salt Lake, Utah, and also in Karst region, where the dissolution and reprecipitation of carbonates leads to the formation of caves, stalactites, and stalagmites. The carbonate class also includes the nitrate and borate minerals, right? Then the category 3 is sulfate class. These sulfate class are anion of sulfate and are commonly formed in evaporatic setting. But sulfates and halides are formed at the water sediment interface by slow evaporation of high saline waters. They also occur in hydrothermal vent system as gangue minerals along with sulfide ores. The secondary oxidation product of original sulfide minerals also come under this class. Common sulfide minerals are, anhydrite, calcium sulfate, celestine, strontium sulfate, barite, barium sulfate, and gypsum hydrated calcium sulfate. The sulfate class also include, the commonly used chromate, molybdate, selenite, sulfide, tellurate, and tungsten mineral. The fourth category is halide class. Halides, like sulfate, they are commonly found in evaporite setting, such as salt lakes and landlocked seas such as Dead Sea and Great Salt Lake. It includes the fluoride, chlorides, bromide, and iodide mineral. This class mainly represent the natural salts such as fluoride, calcium fluoride, halide, sodium chloride, sylvite, potassium chloride, and salt ammoniate means ammonium chloride. The fifth category of that mineral is oxide class. This oxide class includes the oxide and hydroxide mineral. This class is extremely important as in addition to valuable metal. They also provide the best record changes in the Earth's magnetic field. They commonly occurs as precipitate close to the Earth's surface, oxidation product of other minerals in the near surface weathering zone, and as accessory minerals in igneous rocks of the crust and mantle. Example of common oxides are hematite, iron oxide, magnetite, iron oxide. Magnetite is also iron oxide. Chromite, iron chromium oxide. Spinel means magnesium aluminum oxide, a common component metal. Limonite, iron titanium oxide. Rutile, titanium oxide, and ice, hydrogen oxide. The sixth category of minerals is sulfide class. Commonly, this sulfide class include pyrite, iron sulfide. They are called as, sometimes called as fool's gold. Then chalcopyrite, copper iron sulfide. Pentlandite, nickel iron sulfide, and galena, lead sulfide. The sulfide class also includes the selenites, the tellurites, the arsenites, and the antimonites, the bismuthinites, and that sulfur salts, right? The second category of this mineral class is phosphate class. It includes any minerals with tetrahedral unit, where this in this formula you will see A04. This A can be phosphorus, antimony, arsenic, and vanadium, right? By far the most commonly phosphate is apatite, which is an important biological mineral found in teeth and the bones of many animals. The phosphate class include phosphate, arsenate, vanadate, and antimonate minerals. The eighth category of this mineral class is element class. Now, this element class, this group covers native metals and intermetallic elements like gold, silver, copper, semi-metals and non-metals like antimony, bismuth, graphite, sulfur, natural alloys such as electrum, a natural alloy of gold and silver, phosphite, silicite, nitrites, and carbide. Now, these carbides which are actually only found naturally in a few rare meteorites, right? The ninth class of these minerals is organic class. This includes biogenic substances getting concentrated or transformed by geological process. That is oxalates, melitates, then citrates, cyanates, acetates, formates, hydrocarbons. Other miscellaneous species constitute this class. Examples include mullite, melite, pictellite, carfetite, evankite, and abelsonite, right? So another category which we commonly follow is Stern's classification, and it's also very a scheme of division of the Stern's classification also more or less same that of Duna classification, and this also divided into because of dependent that basically based on the families in group according to chemical composition of that mineral and crystal structure of that minerals. There are, I will not go in detail about that. If you look into that, there are elements. If you look to the same, more or less same to that of Duna, there are elements, sulfide and sulfosol, halide, oxide and hydroxide, carbonates, nitrate and borates, sulfate, chromates, molybdate and tungstate, phosphate, arsenate, vanadate, silicates, organic compound. So, So, in this session, what we learn is that we know that there are that increase in mineral demand is scarcity of minerals, and with human civilization, we depend on minerals. This is evidence that some of our that's in our civilization before prehistory and history. It is found that our civilization was named after the mineral like Stone Age, then and so on. So, and we also learn about different kind of mineral deposit, ores and reserve, and we learn as a student of sustainable science. We need to learn about types and grouping of mineral resources, which today we have discussed on all these things. I'm sure with this basic knowledge on this different kind of minerals, how we have to understand depending upon their characteristic, then we will be able to understand what are the possible impact, how to utilize it efficiently in sustainable way. So thank you very much with this session. Let us meet in the next session. Okay, thank you.